Just a quick recap what we did on Tuesday. So we went from quantum mechanics. So then there was a result for the Holm-Coulomb theorem I told you about. And so this gave you some variation principles. So that were of the form so some functional plus an integral times a potential, and so quantum mechanics was something like you minimize over wave functions in quadratic form to get eigenvalues, and then we did a low density limit, or let's say a dilute limit of this f at densities rho, and then we got to multi-marginal optimal transport with Coulomb cost. So we had something like minimum over transport plans and some interaction, so some Coulomb cost subject to a fixed marginal. And so that was the story I did on Tuesday. So so what's my plan for this morning? I want to do one thing that was related to this limit here, which I think is related to regularity, which is a lemma I stated, but I think it's of independent interest, and I think it's totally orthogonal to anything on regularity other people have done in optimal transport, because it wasn't about regularity of optimal maps. So there's nice work by Caffarelli and recently by Alessio Figani on regularity properties of optimal transport maps. So this, but this makes no sense. This is not applicable to this Coulomb cost because we have already seen the optimal maps have jumps, so they have huge singularities. They're not in any solid states. But on the other hand, the regularity we were looking for is of a different form. So whether in this minimization here, whether the gammas can be approximated by smoother gammas. So what I want is not that the optimal map is a Sobolev function, but that the gammas can be approximated by Sobolev functions while keeping it exactly this rigid constraint. So I'm not doing here something orthogonal to Caffarelli and Figali because I don't appreciate what they do, but because it's not applicable to the Coulomb cost, simply because there the optimal maps are not Sobolev maps. I showed you the terrible jumps there. So instead, there's this gammas, and so the lemma is stated. So this is about smoothing under a marginal constraint. So it can be stated as a density statement, and I do it. So if I have rho mu in P of RD, so if you want to take derivatives, I'm going to go in the Euclidean space here. So and then we assume this is in W11 of RD. So then we can take the gammas in P of R D in this, so 2D intersect with W11 of R2D, so which have marginals mu and mu from left and right. So this is a statement really for general marginals, no symmetries, so right marginal mu, left marginal mu. In the standard kind of way, and I claim this extends in this.
But you have a different letter. There you use rho and then you use mu. No?
You're right, thank you. So let's fix mu and mu. I think it's the standard notation for everyone. So the rho I use when they're both equal. Okay, so fine. So note that note that this condition here is actually necessary because W11 is invariant under taking marginals. Yeah, and we discussed if we go to W12, it's the square root set of W12. So this condition is in fact necessary because if these guys, so if I can approximate my guys here, then the approximating guys automatically have to have this much. Okay, then how do you do this? So
what you removed on the second line is the intersection with the.
No, I'm saying I can take any plan which is rough. It's just a probability measure which has the given marginals, but I can smooth it or somehow make it into a W11 function while exactly preserving the marginals. So that's the remarkable thing. I exactly preserve the marginals. So and how could you do that? So the naive thing would be to do so you start so you start from a given gamma which is just in P of R2D and which has these marginals. So now you want to approximate by something smoother. So the standard thing you would do is you smooth this thing. So let me smooth it in a typical way. So take a Gaussian of which epsilon or any other modifier, and I take a gamma twiddle epsilon is something like so. So if we take this Gaussian so and we take the convolution with the gamma. Okay, so and if you take the modifier to the tensor product, then this nicely tells me what the marginals are because the modification pushes on the marginals. So this changes the marginals. So this is a smooth gamma, but it has the wrong margins. Okay. So that's the standard thing. We mess up the marginals. So now I do something to get the right marginals back without losing too much regularity, and that's some of the tricky things. So how I'm going to project this back onto something with the right marginals, and so the first thing is I invent, so the first ingredient is I invent a transport plan which moves something, so which has left marginal mu and right marginal mu tilde. So I can think of it as a stochastic map, so a stochastic transition kernel, which maps a sort of marginal distribution mu to the marginal distribution mu tilde. And so here's how I do it. So this is mu and this is mu twiddle, and so they're somewhat close by. They just differ by a bit of modification. So there are two regions. So one is let me call this f of x is the pointwise min of mu of x and mu twiddle of x. So notice that the marginals here are promised functions, so I can take the pointwise minima. And so I want a transport plan that moves this lump of mass into this mass. And so on this bit I do the lazy thing, so I have to do nothing, so I do nothing. So mass that sits here I'm not going to move. Okay, so I do nothing here, and then I have to move this piece to this piece. But here I have to be careful. So doing nothing also messes up nothing. So doing nothing doesn't mess up my regularity. So on the other piece I have to do something without messing up the regularity. So what I do here is a sort of, so I don't try to do something with a map, but I do a mean field plan. And so this is how I can go beyond Caffarelli and Figali here. So if I try to do a map, I would be stuck because the maps are not smooth. So I cannot apply Caffarelli Figali. It doesn't hold. So I have to do something else. So this is the thing. So I do a mean field plan here. So if you write this out, so the value for this gamma of xy is so I take f of x delta x of y plus, and so now I have to give names to these differences here. So this guy I call e of x, and this e twiddle of x or something. Yeah, so it's mu minus f. So e is mu minus f, and e twiddle is e twiddle minus f. So and now how do I do this mean field stuff here? So I do just the mean field plan. So every point is equally likely to go to every other point. So I do this, and to normalize, I have to normalize by the integral of e. Or the integral of e twiddle, it's the same. Okay, so this is my plan here, and let's check the marginals. So let me just check the marginals. Check that gamma has the marginals. So this gamma, which I know gamma mu twiddle, has these marginals. So so how do we check that? It's easy, but gives a feeling for this. So if I do so gamma twiddle, so dy. So for the first part, I just get f of x integrating over this data function here, and here I get e of x times integral e twiddle over integral e twiddle. So you see why I needed this thing, and so this gives me back the mu of x. And if you do it the other way around, so ex, so you get f of y is left, because this time the data function substitutes the y for the x here if you integrate over x, and then yeah, writing this as stable. Okay, so f of y, and then here, so we get back the twiddle of y, integral e divided by integral e twiddle. But because the mu and the mu twiddle are both normalized, they have the same integral. So by normalization, these two are actually cancelling, and then you get back the mu twiddle. Okay, so here we go. So that's an honest plan. And so now I do something else, which is also not done in books, but transport plans have a beautiful group structure. So there's a group structure sitting here. You can compose plans if they have if the right marginal of one of them equals the left marginal of the other, you can compose them. And so now my gamma smoothed under marginal constraint of xw. So what I then do is I take the gamma from mu to mu twiddle. I compose it with the smooth guy, which maps mu twiddle to mu twiddle, and I then compose again with the inverse of that guy. So the mu twiddle goes to mu. So this guy maps mu twiddle to mu twiddle, so these two smooth marginals, and then these three guys can be composed. And so the composition rule is very simple. So you think of some sort of conditional transition kernels upon passing through an intermediate point. So let's do it for the first guys here. So this so of x y. So I'm gonna have two integrals, a dy and a dz. And so then I take the characteristic function of where mu tilde is positive and divide by mu tilde of y. I need to do that so at the end the marginals come out right. Then I take this plan here, so yz, and then I do another transition. So now the characteristic function of mu twiddle positive of z, and then I can divide by the mu twiddle of z, and then I take the transition with the same construction here, going from mu twiddle to mu. And so there are two integrations. So here I condition of the map going from the transport from x to y to z and eventually to w, and I sort of condition on this path passing through y and z, and then at the end you integrate over all possibilities of the y and z with the right probabilities. So that's the construction. And so this is well, for the Gaussian there always one. Yeah, maybe you want to do a complexity support guide, not to destroy complex support or whatever. Yeah, depending what you want to do. I don't do complex support. Okay, so here we go. So that's the guy smooth under marginal constraint. Once you have realized what to do, then you just check it's still W11, you differentiate. So I've not done anything really singular here. So these pieces are still in a good solid space. Okay, so here we go. So that was this story here with the smoothing under marginal constraint. Yeah.
So then this lemma always works if you have the Sobolev space preserving the marginals.
Yeah, I mean, okay, for first derivatives it works, but taking pointwise minimum is good for first derivatives, but not the second. The first derivative is fine, so it works for, but we discussed, I think, on Tuesday, so
yeah,
the right condition is that the square root of the guys, the 1 over p's power is in W1p.
Yeah.
That's another space that preserves margins.
Yeah.
So, okay, so any question on this stuff?
Yes, so pointwise minimum is good for Sobolev spaces, the first order of the
No, but I mean, Sobolev space is what you want when you calculate variations where gradients appear. So I was interested in first order functionals because quantum mechanics is first order functional. So it involves integrals of gradients, but not more than gradients. Therefore, I was interested in first order. So, if you So here we go. So now,
So then it's taking this density with respect to weak convergence?
yeah, weak star in measures, and presumably also metrics that kind of metrize it like Wasserstein or something.
And so this also works if I understand correctly, if you do not require only one, only for instance L1, and you want to approximate.
Yeah, that works just as fine with L1. In fact, just with this argument immediately gives it. Because this guy is in L1.
Yeah.
So when you do the integrals, so of course to see this you have to do the integrals here more explicitly because this big integral still has the data pieces. But I mean the L1 times data function convoluted with the data function gets L1. Okay, so here we go. So okay, yeah, that's. I hope you don't force me to do it on the board now. Okay, so that was this stuff about smoothing under marginal constraints. So it might be useful for numerical schemes or all sorts of other things one wants to do. Or for example, it will allow you to replace the rigid marginal constraint in optimal transfer by a soft constraint by penalty. So it would show convergence of a penalty method or lots of stuff. So here we go. So now I want to do something else and give a quick. So now I want to do a little excursion in so I'm going to go to physics for a little bit of rather chemistry. So thanks. So that's a little excursion on this physics, so on the stuff that motivated me. So, but I thought I'd present a little bit of this here. So because this density function theory, so it's a big field in chemistry, physics, material science, molecular biology, and so in these simulations. So we looked at somehow, so the optimal transport comes in because it gives you some version of modeling the interaction energy of a system when you know its single particle density. And so it gives you one particular model for that, which may or may not be good. We'll see in a minute, but there are certainly circumstances where this is a good thing to do. And so what you want to compute in these simulations is the ground state energy of a molecule, the electronic ground state energy. So, and it's by minimizing three pieces over this density. It's a approximate kinetic energy, an approximate interaction energy, and the exact interaction energy from an external potential. So, so let me go through these remarks in not in the order in which they're written, but in which we can look at the formula. So let's look at this line here. So the first two pieces are molecule independent. So you approximate them once and for all molecules, for all of chemistry. And this piece is chemically specific. It's molecule dependent, but in a very simple and explicit way. So the external potential of the electrons is just the Coulomb potential exerted by the atomic nuclei. And it depends on the charges and the positions of the nuclei. So this is so basically by varying the number of atoms and the number in the periodic table, you model any molecule you want, including DNA or whatever you want. You model this way. So in that sense, this is not a specific model for one particular molecule, but a universal one for all molecules. And so why do we want this E naught? So we also talked about on Tuesday, because the E naught, it will depend in particular on the positions of the atoms, on these R alphas, and if you look at it as a function of this, it encodes the chemical behavior. So one key quantity you want is the binding energies, so who binds with whom, with what energy, and I showed you on Tuesday how you extract it from knowing the E naught. So that was some of the depth of the potential where you have here. So, and then it's sort of routinely used for this reason by lots of people. And so why does one go into this? Well, there is in fact a better model for the ground set energy called quantum mechanics, which is a great fundamental model. But there you need to minimize over electron wave functions. So if you have n electrons, we said even for H2O and 10, you have these many particle wave functions, and they live 1 r to the 30 for H2O, so it's not discretizable. It's not the first dimension. So you have an exact model, but you can't use it because it's too complicated. So therefore, one approximates by min over the, one remodels the system in terms of the single particle density, and you have no curse of dimension, but you make a modeling error because these two pieces get somehow remodeled. But now the guy who systematically initiated this Nobel Prize for it in 1998, and really so now I want to show 3 examples how this approximate function is improved over time. So there's not one good choice, but they improve over time, and hopefully they keep improving.
Yeah. I mean, you explained last time there is an exact non-approximate version for t plus e.
Yeah.
But that's really for t plus e. It's
No,
not
it's
just
for these two, no, and for this. So there is an exact the DFT model for the sum of them, but the trouble with it is it again uses a min over the
Yeah.
sine.
But I mean,
Okay, you're worried about the
there's-
sum.
yeah.
Well, okay, let's say the exact thing is a joint thing for these two.
Yeah.
So for
it's
the
not
T
obvious
plus-
that you can exactly separate that.
yeah, but you could so by the same way in which I define the paradox. Okay, so here we go. So at the sense this curse of dimension is so bad. So you trade a curse of dimension for a curse of modeling, and the curse of modeling, at least you know what to do. So you try some good guess for these guys here, and then you can do numerics. And the curse of dimension, it prevents you from getting any prediction. You simply get no prediction. So this curse of dimension is really bad. So now let's see. So now the first guy who had a decent approximate interaction energy was Paul Dirac in 1930. So long before today's guys. So here's a nice paper by, so he emphasizes he has a PhD in the paper, just in case somebody thinks he doesn't. So Dr. Dirac, note on exchange phenomena, Thomas Atom, and he also puts his, so if you know England, I mean, it's interesting, he puts his college affiliation, not his university. So the university is actually Cambridge. So it's not Cambridge, but he puts just his college. So he's from St. John's College, Dr. Dirac from St. John's College. And so Dr. Gero from St. John's College writes, for dealing with atoms involving many electrons, the accurate quantum theory involving a solution of the wave equation in many-dimensional space is far too complicated to be practicable. So he talks about the curse of dimension 50 years before mathematicians.
The practical means for him that he can't have closed form solutions.
No, I think there were already people trying to do numerical or other ways of generating solutions, Hartree at the time.
Neumann ladies.
It was before von Neumann. Neumann got into a little bit later, but Hartree was into it as well. So, and then he says one must therefore resort to approximate methods. So I think so for your own historical picture of Dirac, so Dirac is often presented as a guy who tried to make quantum mechanics more exact by reconciling it with relativity theory, which is something that he also did, but he also tried to make quantum mechanics more approximate by getting rid of this curse of dimension. So he was looking in all directions. And yeah, I think now it will be debatable where his contribution was bigger. I think he contributed both. So now here's the approximation. So there's a sort of near field term. Yeah, like in my near field plan here. Yeah, so and then there is a term. So for the correction, so you take the densities of the electrons with different spins separately and some other spin. So in a sense, but I wanted to show you the precise thing. So it's spin sensitive. So in a polarized system, you have a slightly different energy than in a spin neutral system. So if you put the system in a magnetic field, you change the correlations. So okay, so that is his formula. And so now let's look at the citation history of Dirac's paper. So here is 1948. He wrote it in 1930. So 1930, the scale is approximately here. So there were a few papers I tried to research. I think Fermi cited it in 1932 or something. So some guys cited it here, but it's not online. And so then it approximately stayed close to zero until 1970, and then there was a smooth transition, and then since 1990, for the last 20 years, it has been at 50 or 60 citations per year. So it's very silent, and then it goes up. So basically, if you approximate, you can approximate this by a Heaviside function, which goes from 0 to 60. And then if you take the derivative, you get the Dirac data. Okay, so it's a nice citation. So in case you ever blamed by your supervisor, hey, you don't publish enough, or your paper is not cited, or whatever, you show them this graph. Or if you're a more senior guy and your department head says, well, you haven't published much, so I don't give you a pay rise. You just show them this paper, the citation.
Okay, so they will say that Dirac published a lot.
Hmm?
They will say that Dirac published a lot.
Actually, he didn't. He doesn't have so many papers, but he has good papers. So that's the thing. So now there's another approximate energy. So this is from 1988, and it's actually much more messy than Dirac's, but it's better. And so I also show you some citation counts. So look at this number here. That's a citation count. Anybody in this room? I don't.
This is one thing. And this is one thing.
It's just one paper, yeah. It's incredibly highly cited. So it shows you the number of people which are doing simulations. So he says current gradient corrected density function approximations of the changes. One part of the interaction fail to reproduce the correct blah 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 behavior of blah blah blah. Here we call it the correction. So okay, so it's a very clever paper. So it has this series of citations. So here is Becky's paper. So I just want to show it to you to see what people do in current simulations. So on the one hand, so you keep the first term, then you keep the Dirac term. So with this number here, so with this piece gone and this piece gone, you get back Dirac. But this piece is a correction. So somehow that accounts for the fact that when you have an inhomogeneous system, so Dirac derived it for some homogeneous electron gas, and so when you have inhomogeneities that change the correlations, and there's a funny term here with a Sinch inverse and Mark, you had a magic hand on Tuesday, so magic hand today. Press hard, okay. Mark's the real man. So here we go. So here's the Sinch inverse, and this is another piece that didn't get added by Becky, but by Walter Coulomb, the guy with the Nobel Prize. So the correlation energy density of a homogeneous gas of density rho. So that's a reference system you study numerically and asymptotically, and then parameterize. So you pretend the system is locally behaving like a slowly varying gas with slowly varying density. Then this is a reduced gradient, and this is an empirical parameter which she fitted to some data. So I mean, it just looks messy, and so if you want to think about nature, so real electrons don't know about this term. They're not trying to minimize this term. They don't know about it. But for us, it's a convenient way to give some approximation that that gives good results. So now let's show you some
sigma. So it's the sigma.
The sigma was the spin as usual. So you summarize it. So the sum of the two spin states. So you keep track of the upspin electron density and the downspin electron density. So the spin dependent stuff is kind of trivial, but it changes. Okay, but it is sort of messy.
So it's doubles with degree of freedom. So doubles with degree of freedom.
Yeah, which in terms of when we're talking about crystal dimension, we couldn't care less. So we're worried about factors like 10 to the 30, but okay. So now here is the binding energy. So binding energies versus experiment. So let's say one example. So for O2, so O2 is my mobile company. So I chose O2 for some reason. I can't remember. So for O2. Wish that did. I think it's not as many people are listening to me as are in this room. This is for them it's not good attitude. So to get the binding energy, you take the ground state energy of O2, so the lowest energy of this combined string. So O has 8 electrons, so O2 has 16 electrons. Each electron has 3 position coordinates, 16. Sorry, no, not. Okay.
48 is
Yeah, it's 48. So you go into R to the 48 because 48 is 3 times 16, and then so to get the energies of the 2 atoms separately, you take twice the ground state energy of a single atom. So that is an eigenvalue of a PDE in R to the 24. So and then you subtract these 2 numbers. So now this is kind of pretty hopeless, but you cannot do this at all. So now that with this package, so here's what you get. So first of all, this is what true binding energies look like. So this is experimental data. I'll show you Becky in a minute. These are experimental data, and so if you, so I think this graph is really very important in chemistry, and unfortunately not in school books, but it should be in school books because there's huge differences in binding energy. It's not a so chemical specificity is not a small perturbation of something constant. So it's huge. So for example, if you take the elements with atomic number 3, 4, and 7, so lithium, beryllium, and nitrogen. So they have atomic number 3, 4, and 7. So if I change the Schrödinger equation, I change the nuclear charges from 3 to 4 to 7, and the electron number from 2 times 3 to 2 times 4 to 2 times 7. So these are very small changes, all around changes, and the binding energy is in the ratio 10 to 1 to 100. 10 to 1 to 100. 10 to 1 to 100. So even going for the first few elements, you get differences by a factor 100 in binding energy. So this shows it's an extremely tough problem to predict a curve like this. But this is what you want to do in chemical simulation. So now let me show you how the Becky 88 does, and that's some of my explanation for these 30,000 citations. You get a pretty good match. So N2 is somehow spot on. O2 a little off, F2 a little more off, lithium is a little below, H2 a little above, but it really gets this chemical variation right. And so that is crucial in simulation. So what is particularly crucial is the ordering of the binding energies between different elements. So you see correctly that F2 is more strongly bound than lithium 2, and you know, H2 is similar to O2 but a little weaker, and so on. And that's the crucial thing that decides the chemical Lego game. So when I'm an atom, I look for a partner who wants to bind strongly to me, and to find the right partner, I need to get the ordering of these bond strings really right across the periodic table with some universal thing. And so for some reason, this damn Sinch inverse does the job. So that's in mind, damn Sinch inverse.
So nobody's interested in calculating binding by C2?
Well, I think so. I didn't find that. So I think Gero Friesecke was too lazy to look for values for all of them. So it's tricky to find, because if you compare them, you want one simulation with the same numerical basis set and blah blah blah. And so
This
this.
would be interesting to see.
So these green dots were simulated by another very good quantum chemist called John Coulomb, who also has a Nobel Prize, but he used Becky's function just to test it. So it's a very careful test and super guy. And I think nobody is interested in calculating helium-2 and neon-2. It might be difficult to find values because they can't combine. Beryllium-2, people don't show it because usually they get bad results, so weakly, and boron-2 and C2, they're just in the literature. Okay, so here we go. So that's that. And then I want to show. So another part of the story would be when you use the interaction energy of optimal transport. So this guy here. So which we're discussing here. So and I thought here on this slide it's taken from a paper by us recently in 2014. And so this is done simulations in my group in Munich by Wojciech Chen and Chris Mendel and myself. So here is so for H2 you can compute the energy curve exactly because it's low dimension. It's now 6, and that would be standard. That would be a standard density function. It's not the Becker 88, but it's another standard one. And this would be the SCE stands for strictly correlated atoms. This is the optimal transport. And and in fact, so we compute numerically this optimal map. So if some density here is mapped to here or whatever, so you see a little bit how the map looks like. So here, so we use this optimal transport energy. And so one thing about it is it looks like it has a curve dimension, but it doesn't because we can make this Morse ansatz, and it's not fully rigorously justified, but for 2 particles it's rigorously justified by us, and for n particles in 1 dimension it's rigorously justified by Coulomb, De Pascal, and Di Marino, and everybody believes it can be rigorously justified in general. It's just we don't have a proof at the moment. But this formula is believed to be correct. So then there is no curse of dimension because you're looking for n-1 maps from R3 to R3. So the storage cost is linear. And so that's one nice thing, it has correct asymptotic behavior at large distance. And that's not an accident, so we also put a proof of that in it. So we managed to put one proof in chemistry papers. As an appendix. And the rest was about simulation. So you see that in certain regimes where correlation are kind of important, even this spare thing, it does quite well, and in certain regime at a long interatomic distance, it beats standard functionals. This is actually better. But so at equilibrium is worse, it really underestimates the interaction energy. But so the true thing to do in the future is sort of looking for better ways to don't just take a limit, but look at somehow sort of improves this mathematically by looking at the right corrections when you do the asymptotics from quantum mechanics.
So why should one expect that at large distances these things become grand?
Oh, okay. So why should one expect this? So this has to do with the fact that at large distances. So let's say for H2, the game is governed really by interaction, not by kinetic energy. So the single particle density kind whatever. So this is set by the other terms in the energy, and then so for H2 when you dissociate, you get a purely ionic, purely neutral configuration. So whenever one electron is on atom A, the other electron goes to atom B, or vice versa. But they're never at the same never on the same particle. So anything that starts from mean field is kind of wrong, because mean field for a dissociated H2 tells you when one electron is at the first atom, you have a non-zero probability of the second electron also being there. But in practice, the second electron never goes there. If you look at the Schrödinger equation and do some rigorous analysis, you find it's exponentially smaller than the distance. So the probability of these ionic configurations, which is basically an H- and an H+ instead of 2 H's, is exponentially smaller in the interatomic distance. But when you start from mean field and then you try to add corrections of mean field, you will, I mean, your correction first of all has to subtract the whole mean field thing, and it doesn't make sense in sort of perturbation theory. And so in the sense that this is related to the point I learned from talking to Claudia Kluttberg, my colleague in Munich, and Friesecke, always said, okay, I mean, why do people start from mean field? That depending on where you want to go, there might be a much better starting point. Instead of mean field, might be complete anti-correlation or something like this. And so this is H2 is an instance of that.
But I mean, still, they would then need to have that when you look at one single item, and forget about the other.
Yeah.
Then your OT approximation should be exact.
Yeah. So I haven't told you what I did for the other functionals. But I took a pretty good one for the T here. So I took the same aspect for the T. So for the T, you take something quantum mechanical, which involves gradients, which in fact all the people I talk about, like Becky or so, they will take this T, which goes back to what I call. So I think I want to get rid of this stuff here now and do something with this. So, which I think ties in with this. This was not into the thread, I think. So, yeah, so the other thing I think I wanted to do is sort of so it's some calculation that so far I've been applying optimal transport philosophy to a problem in physics. Now I want to do something in the opposite direction, re-look at classical stuff in optimal transport from a physics perspective, and exactly this physics perspective that comes from these Hohenbeck-Kohn theorems of minimizing under constraints and blah blah blah. So interestingly, you really see something new about OT this way, or I think it's new. So I'm sure these founding fathers like McCann, Gango, Jan-Brenny, and Villani, they have some sort of understanding of these things, but it's not visible in the books or in the papers or in the way the proofs are done. So I think it gives a simple and nice angle of OT. And what I do so essentially is is my interpretation of stuff that was done by physicists who at the time did not know they were doing anything related to optimal transport. But Mike Sadler, Paula, Corey, Georgi, and Andreas Salin. Is in Paris, and so Paula is in Amsterdam, and Mike Seidel is in Germany, in the University of Regensburg. So 2007, and so our take on this is in the paper by Guoqi Chen and Chris Mendel, and this is so here's here is sort of let's say it's a physics perspective of T, and so the standard thing problem is basically you have min or some optimal plans, and you have some interaction gamma, and so rho is a given marginal, and you minimize over over the transport plans. And then there's also something called the Kantorovich potential. So it's the sum over b of x plus v of y less or equal to L of x minus y integral v times rho. So this would be the kind of dual problem in OT. And so there are two questions I want to ask. So the first question is, what is the physical meaning of the Kantorovich potential? And the second question is, so why do we have the magic Gango-McCann formula? So why do we have the magic formula that the optimal map is like x minus the gradient of the Legendre transform of the gradient of the potential? So where do these things really come from? And so this is sort of my take on this. So so the first thing is you introduce the Legendre transform. So it's the sum over rho integral v rho minus v of rho. Okay, so I forgot to introduce a functional here. So it's very useful to study to look at the minimum energy of optimal transport as a functional of the marginal measure. So this here is the minimum energy as a function of the marginal measure. So the least possible amount of interactions energy any plan can somehow have under this given marginal constraint. And the key thing is here to think of L of x minus y as an interaction potential. Here's x and y, and then it's quadratic thing of some spring or whatever between two particles. Okay, and so then now this is some kind of minimal interaction energy as a function of the marginal measure. So then
and it's convex.
Sorry?
Is it convex?
Yes, as a matter of fact, it is. In fact, this is the next. We're going to use it in actually 30 seconds. But since you remark it, we might as well have it now. V is convex. So very simple to show. And then therefore, if something is convex, it's equal to its double Legendre transform. So now now I introduce the Legendre transform. So no fancy things happening here. And so now let me write minus v star of v. So now I do something that is less trivial. So now watch this very carefully. So this is related to what we did in the Hornbeck-Kohn theorem. We had an unconstrained minimum, but we replaced it by a constrained minimum by a constrained search. Now I'm going to do exactly the opposite. I take a constrained search thing and unconstrain it. Okay, so it's the inverse procedure that leads to the exact Hornbeck-Kohn. Somehow I'm playing Hornbeck-Kohn inverse at the moment. Okay, so we start with V. So it's minus inf over rho integral so so and now we remember what the V was. So I make this a double inf, so it's a minus inf rho and an inf over psi over gamma with marginal rho. So now I think the minus sign we can now get rid of because I put it here. So I take everybody happy with my minus signs. Okay. So I do the double inf here, and then so this would be so I can now write this as so it's the L of x minus y d gamma plus and so now this thing here I can also rewrite when the gamma is marginal rho. I can rewrite it as minus v of x plus v of y. Okay, because when you take, so this is the integral over x and y, and then over the other variable it passes just from the margin to the rho. And I think the normalization here is good to use the physicist normalization, so gamma x y is rho of x halves. So the x is rho of y halves. So you get an archive, but then you get the sum here, otherwise I would have to halve this. So, and that's a cool thing to have, because now I'm going to use the double Legendre transform. So the key point here is so this is basically now the inf over gamma over a general probability measure with no marginal. So that's the key point of this exercise. So I've gotten rid of the marginal condition, and now now what is this good for? Now by the convexity we can now take the double Legendre transform. So W2 star of rho, so it's the sum over V integral V times rho minus star of V. And so it's the sum over V, and inf now okay, so now let's now do the equation here I get. And so now let's look at the nice fact here. So this is basically the same as the V of rho, because it was convex, and I took the double Legendre transform. Now, if the V is the maximizer of this. So V is the maximizer of 1. Yeah, so this gives you a sort of dual potential. In fact, you can show this is exactly the same as the Kantorovich potential, but you can also think of it, either think of it as an alternative definition of a Kantorovich potential, or think of it as a reformulation of this. So maybe this formulation is conceptually a little messier, but I think this one is nice. So it's an alternative definition of a potential in this problem, which actually gives the same, but regardless of if it's the same or not. So then, so we can say something about the minimal gamma, because then the gamma that's associated with V here is the same as the gamma that solves this problem here. But this problem is much easier, much easier. Why? So gamma is the minimizer associated with V of rho. So in the variational principle for V of rho, so let's say of variational principle for V of rho is the same as gamma minimizer of the variational principle for W2 star of rho. So and now, but this thing here we can minimize out. So I'm just integrating a fixed function against the gamma. So here is x and y. Here is my my function. So this would be L of x minus y minus d of x plus d of y. And so when you integrate a fixed function against the measure, how you can minimize that? You put a mass on the minimum. So we put a mass on the minimum, so the gamma needs to sit here. So it needs to sit at the minimum point. So the support of gamma needs to be in the set of minima of the function L of x minus y minus d of x plus d of y. Okay, but if we know from so Michael, we were talking about Fermat in a different context, but he also realized there's another Fermat's theorem, namely the gradient of the function vanishes at a minimum point. It's also due to Fermat. So I will use this easy Fermat's theorem. So this tells me here that the gradient of this thing vanishes on the support of the gamma. So grad x L of x minus y minus grad d of x is 0 on the support of gamma. So and now what we're going to do is if we now do if we now have an optimal plan in the way we discussed on Monday, or it's not an optimal transfer, you have this structure with the plans. So if we have that the optimal plan is of the form marginal of x, so in this case half for the normalization and delta t of x of y. So if we have an optimal map and the thing looks like this, so Marvel was mentioned in the pictures when here is x, here is y, and the gamma was supported in some linear lines. Yeah, so y equals t of x. So when we have this typical map structure, then this takes that the gradient of L at x, so gradient of x minus t of x, equals grad v of x, and now over there, so on the support of the rho, because whenever the rho has support, whatever the y equals t of x is when the gamma has support. So now we got this formula just from the picture there. And so now I claim this is the Gero-Maclan formula. So this is Gero-Maclan. The only difference is I'm expressing grad V in terms of T. So if I solve this equation algebraically, I can re-get the T in terms of grad V. So this is Gero-Maclan. So except we have grad V in terms of T, not vice versa, and we don't need any convexity. So this has nothing to do with convexity of L. So convexity comes in because it gives you invertibility of the gradient. In fact, you don't need convexity at all. Invertibility of the gradient would be enough to invert. And the whole thing has nothing to do with convexity, can be done with any interaction potential. So now my two questions from the board I can now answer. Sorry.
So V has to be convex, right?
Sorry?
So V has to be convex.
Capital V.
Capital V.
The capital V has to be convex, but this has nothing to do with the interaction being convex. What Gero and Maclan is the cost, what they call the cost is convex. This has nothing to do.
But the difference is between different types of convexity, right? When you say convexity, you mean additive to
As a function of distance. Yeah, so whatever.
No. So V is convex.
No, I mean the C. So in these papers, so which is the cost. So this is done for convex costs, like power costs. So that's what I'm saying. And so that's what can be used to invert this equation, with the Coulomb transform techniques and so on. But this has nothing to do with it. So to me, this obscures the main point why an equation like this. So my viewpoint is first derive this equation and worry later about whether, so first of all, it's not clear whether it's better or worse to express T in terms of grad V or vice versa. They're equally good. And then you might as well take the formulation that's more general and requires less assumptions. And so also now I'm going to come to the physics, to the interpretation. So this also gives me an interpretation of the Coulomb potential, which is why I spent all of Tuesday, hopefully not confusing you too much, but with this kind of semi-classical stuff, with sort of kinetic energy disappearing. So if you think of particles, forces in the semi-classical picture, then so minus grad V of x is the force exerted on the particle at x by a particle, I could say by a particle at t of x, or even better, I could say by the other particle, if the system is in a strictly correlated state. So by strictly correlated state, I mean that the pair density of particles is given by the gamma, by the optimum plan. So the answer is that the V has no physical meaning, but the grad V has, and it's a force. So the right thing to relate to the optimal maps is the force. So this answers a bit the question why gradients. Yeah. So why was the optimal map a gradient? Maybe there are ways of understanding it from Renier, but I didn't understand it from Renier. So
can you give an example of a V that is convex without the cost being convex function of the distance?
yeah, okay, the Coulomb is the thing.
Yeah, but it's a
it's not but the cost is convex in the row, but the Coulomb is not. So this the thing of most interest to me is not convex. So if this is if this is x in R3, and so this would be 1 over absolute value x. So it is not convex.
But it's still a convex function with this function.
Yeah, but it's not convex. So what you need for Gango mechanics is convexity. Get me away from convexity in the distance. Maybe you want to talk about this, but I'm talking about what these other people talk about in literature. So they say the C is convex.
Okay.
Not that it's a convex function of distance. It's a deep fact due to our co-workers or myself that you can get a theory for these potentials. But this is not trivial and uses this philosophy here. Okay. So here we go. So nothing to do with convexity in the distance. It's because you don't take the gradient, you take the gradient of the edge simultaneously with respect to all coordinates. So in some direction it's convex and others is convex. Every point is a second. Okay. So now I wanted to okay, yeah, so it's a gravity is a force. And so in a sense the V, so we could say the V is an effective one body potential. So by one body potential, I mean it depends separately on x and y, but not not jointly. So just each particle in the system feels the same potential, which emulates the effect of interaction. So, which is a two-body potential. So you construct an effective one-body potential, which exerts the same force on particles as the many-body potential. So this is what's going on. And so let me just finish by writing the examples. So sort of example one of my formula here. So I'm going to write some example for the formula about is it.
When you say it's a two-body potential, but it's special in the sense that the optimal transport context allows you to, or forces you to connect to exactly one partner and not to all the other ones. Whilst in the usual two-body potential statistical mechanics context, you would be doing the opposite, where you connect to every single partner.
Wait a minute. So I've done it for two bodies. So wait, I'm gonna write something for n bodies. So this.
I don't know what I mean is in your.
So that's why I said it's emulate this. So it emulates this effect in the strictly correlated state.
But
so that's what I'm saying.
Yeah, but you're taking a different n. My many particles are all the other elements represented by the same in row. And you connect.
Yeah, but that is not related. You can now. I mean, you can do two rows. So that's not related to that. So it's really trading a two-body for a one-body potential by going into a region of specific states. And so, I mean, the first example I want to mention, so you get the Grenier formula back. So if you get L is like x minus y squared halves, so we get so this formula then becomes particularly nice. So my formula here is so we get sort of grad L is the identity. So then we just get x minus t of x is grad B of x. So this is the Grenier formula. So if you do x minus y to the p over p, so then basically you can show so then what was the formula here? So if I take the gradient there, so I get x minus t of x to the p minus 2 times x minus t of x is v of x. And so this is basically the same as the McCann-Ganneau formula. So an easy exercise for you would show if you solve this equation, you can solve easily for t in terms of grad v by computing the link, taking the absolute value first, and expressing the absolute value of that in terms of the absolute value of that, and then substitute. So this equation is just an algebraic thing, and so this gives you exactly that. T of x is x minus grad v of x to the e prime minus 2 times grad v of x. So which is x minus grad a star of grad v of x. And you do a star is x minus y to the p prime over p prime. So with the usual duality. Okay, so if you invert this, you get exactly this. And so for the Coulomb, you get a nice version. So for Coulomb, you get just for the Coulomb, we get for the Coulomb we really get a nice physical formula. So we get so grad v of x is x minus p of x divided over x minus p of x cubed. So if you have so the grad v, if the t of x is here, so it's exactly the repulsive Coulomb force. So exerted on the particle at x by the particle at t of x. So it's exactly the repulsive Coulomb force. And so this formula is much nicer than the one we derived earlier. So so we derived one using this Langmuir-McCann formula, but then it looks messy and there's 3 halves. And it looks much nicer here. So so if you solve for the t of x, is like x plus something like grad v of x over grad v of x over grad v of x to the 3 halves. So this is the formula we derived earlier, but I mean this is much better, and is actually in the paper by the physicists who didn't know they were doing optimal transport every time. So and it's the same formula. And so now the final thing I want to say about this works for many body T. So if you have many particles or something like this, so x, and you have these other guys here, Ti of x, other transport maps, so for multi-marginal, you just sum. So grad v of x is the sum I equals 2 to the n x minus Ti of x over x minus Ti of x cubed, where, so in this case, the gamma is somehow like rho of x1 over n delta function at t2 of x1 of 2 over delta function tn of x1. Okay, so this formula, so this way round, it generalizes immediately to multi-marginal. Whereas the Ganneau-McCann doesn't, because then you're really stuck with solving for the t's. So I think so. This was now about the backfeed from sort of re-looking at OT from the point of view what you learned from the physics, and so I think it's so I guess some of the math workers in some way or other will no doubt have been aware of some of these formula in some context, I don't know, but I've not seen any interpretation on this as a force or something like this, or any systematic discussion. And so I think this viewpoint really clears a bit up what is the V. So so the grad of V gives you the force exerted by particles at the locations of the transport maps, and that's somehow the summary of the story. So yeah, thanks for listening. So in the afternoon, I want to go to large N, and then I become more probabilistic, because then I will use methods from probabilistic theory. So no more physics, I think. So this afternoon, it's about probability. Yeah, thanks.